Suppose there is a nonlinear differential equation like this. I don't think there is any algorithm which can be used to solve this kind of complicated nonlinear differential equations. So again, we have to use block diagram to model the nonlinear differential equation. And the key point here is to solve y and to move this two terms to the right hand side. And finally, we can express the signal y like this. And we can see that this part is the input. This part is actually a transfer function. And how can we model transfer functions? It is not quite easy to model transfer functions. So we have to define the signal of this and the signal of this, and then we divide these two signals. So the final block diagram of the system is something like this. And you can view it in this way. This is the input signal. This part is actually the transfer function, but I use the fractional order differentiator blocks here. And this is the transfer function, and this is the other term. I don't think I have enough time to explain them in detail. I think it's better you can read, you can compare this block diagram with the original. Oh, I have already listed the transfer function. You see, 3 times, so we 3 plus this part. And since this signal is y, we have 0.2 times y, the derivative of y, which the order is 0.8. And this part is 0.9. To the order of 0.2. So these 3 blocks will establish the denominator of the signal. And this one is the numerator of the signal, so we can divide these 2 signals to form this part. And this is the input signal. We can assign that the gain, the amplitude is 5 and the frequency is 10. And for this part, we have to construct the inner part first. 2 times y to the 0.7 of the derivative, and then we can use the ABS block, and then power is 1.5. So this is a description to the original system, and we can use this description to perform simulation. And this is the result for nonlinear system. And we haven't obtained the result earlier for this this equation, so we cannot say this one is correct. So the most important step here is again validation. How can we validate the result? So there are a few methods to validate simulation results for nonlinear systems. One is to change the simulation parameters. For instance, we can change the relative error tolerance. We can reduce the size of relative tolerance, just like in the case of n4.4-5 function. We have to change the tolerance and see whether we can get the same result. Or we can change the algorithm in simulation. We can change it from ODE45 to ODE15S, for instance, and see whether we can get the same result. And the other method is to change the parameters in the filter. For instance, we can change the orders of the filter, or to change the frequency filter range, and see whether we can get the same results. If we can, we say that we get the correct result. If we cannot, we have to perform simulation and change this properties or parameters again.